ARIES is a fault injection framework for quantifying the fault tolerance of deep neural networks. ARIES is an application-level tool with a modular, easy-to-extend interface that enables efficient evaluation of both training and inference under different types of faults. In this demo, I'll discuss recent extensions to the ARIES framework that are now publicly available at this link. I'd like to give a shout out to Ted Pine, a Harvard undergraduate who has helped us to expand the capabilities of ARIES. The first extension I'd like to highlight is that ARIES is now additionally implemented in PyTorch, and fault injection may be performed on either CPU or GPU platforms. The types of faults that can be modeled using ARIES are extremely flexible. Anything that can be mathematically expressed as a manipulation of the weight and/or activation values can be evaluated for any arbitrary DNN. For example, bit-level manipulations such as uniformly random bit flips, or more complex models such as evaluating the impact of emerging non-volatile memory technology. The interface to define your own fault model is quite flexible, and we leverage it to simulate other optimizations, such as quantizing, clustering, or pruning the model weights, and even storing the values in different sparse formats. ARIES can quantify fault tolerance of both the weights and activations of DNNs during both training and inference. Additionally, for recurrent network layers, the user may inject faults into the hidden state vectors. The ARIES framework provides dataset preprocessing and model definitions for a variety of DNNs, though it takes just a few lines of code to incorporate new DNNs or your own models into the framework. An additional feature is that ARIES allows the user to easily study the impact of a given fault model across different data representations and precisions. Let's take a look at an example of how to use ARIES. We provide scripts to easily run a fault injection experiment specifying the model, the number of trials, the type of fault, and the hardware platform for execution, and more. This highlights the flexibility and efficiency with which a user can evaluate design choices and different fault modes for DNNs. The code is organized into deep learning models and experiments, where experiments provide sweep configurations and examples for how to do training and test injections, and DL models is further divided into model definitions and transform definitions. The provided transform definitions include example fault models and quantization. Let's look at some quick examples of these sweeps that you can do with ARIES. It takes just seconds to set up an exhaustive sweep. Here we vary the bit error rate on the hidden state vector values in a recurrent neural network. It's done in 3 steps. First, we define which parameters we'd like to modify. Next, we automatically generate an experiment definition for each parameter setting. And third, we run all of the configured experiments, either in sequence or across multiple machines. The result of the experiment will look like this. As we vary the bit error rate on the x-axis, the overall accuracy of identifying spoken digits across 10 trials is shown on the y-axis, and it degrades as we increase the bit error rate, with the highest tolerable error rate before accuracy loss marked with this blue line. We can repeat this process for any arbitrary combination of fault model, DNN, and injection modes, such as this example performing weight injection on ImageNet ResNet 50 during inference. The up-to-date version of ARIES is still under active development. We encourage folks to download and use ARIES today, and to let us know any feedback they may have. Thank you.